This is the traditional view of the capacitor. Here we have a parallel plate capacitor, and we can calculate the capacitance, we can charge it, and we can calculate the total energy in the capacitor. This is the transmission line model of the capacitor. The electric field in the capacitor is forward and reflected power, as in the transmission line. And here we can calculate the forward power, we can calculate the reflected power, and we can multiply the forward power with the time it takes for the signal to go one way on the line, and the reflected power to go back on the line, and the total energy is exactly the same as with the traditional view of the capacitor. This is what a capacitor looks like for a mathematician: a container for charges, and we get the exponential charging curve. But is this really correct? We will make some measurements here. We will start with a resistor of 450 ohms and connect a capacitor with a characteristic impedance of 50 ohms. All capacitors can be seen as short transmission lines, and the transmission line has a characteristic impedance. We will measure the voltage at the terminals and see what's happening. This is the voltage from the pulse generator. I have 400 plus 50, 450 ohms here, and I connect the cable capacitor. And this is the charging curve of the capacitor. First, we have voltage division. 10% of the signal is going out on the cable, 10% is coming back, and of this 10%, some of it is reflected out back, and this is coming back, and it goes back and forth like this. This is the staircase voltage we get when we charge a capacitor. The voltage here, as seen on the oscilloscope, first we had voltage division. 10% of the voltage is traveling out as a forward signal on the capacitor cable, and it's reflected back, and when it comes back, some part of this is re-reflected out on the cable. So the second step here is higher than the first one, is larger than the first one, and this signal goes out and is reflected back, and some portion of that is re-reflected together with what's coming there, and like this it goes on. And this is an infinite series of smaller and smaller steps. We get this staircase voltage, which of course gives noise on the signal. It's not smooth, it's noisy. But usually the length of the capacitor cable is so short that we cannot detect this noise. But in some applications it can be heard. It can be disturbing. Okay, the next measurement is when the internal resistance is lower than the characteristic impedance of the capacitor cable. What happens? We should measure the voltage at the terminals, but we shall also measure the voltage between the capacitor plates. We will measure at the end of the cable, because here we can only see what's happening at the terminals, not within the capacitor. And this is very interesting because switched power supplies, this is the mains voltage, and this is the power switch. And if the switch is closed when the mains voltage is at a top voltage, we will get a very steep voltage step going through this very little resistor, the diode in the forward direction. And then we have a capacitor here. And what will the voltage be between the capacitor plates within the capacitor? That's interesting. We have the generator with 50 ohm internal resistance, and this is a 300 ohm twin lead. I connect the cable to the output and I measure the voltage at the terminals, and we see it will raise to approximately 85%, and then it goes back and forth like this. This is the voltage at the terminals. Now, if I use the second channel on the oscilloscope, to measure, well, we can see that the amplification of the second channel is exactly as the first channel. And now I connect this to the end of the cable. And this is a picture of the voltage between the capacitor plates. It will raise to almost twice the terminal voltage. We saw that the first step was actually 85% of the voltage, for instance over here. And this voltage goes out and is reflected back. So the top voltage within the capacitor will be 170% of the terminal of the mains voltage, of the generator voltage. And when it reaches the low resistance over here, it will be reflected with a negative reflection coefficient, meaning that the voltage will be lower. So what's happening here inside the capacitor is never seen on the terminals. Usually, electrical equipment, the power supply will break down at power on, and that's because at power on the voltage within the capacitors are almost twice the mains voltage, and usually the capacitors are not chosen to sustain so that very high voltage. Now, when we know what a capacitor is, we shall use it to study a charged particle. Start with a capacitor. The traditional view of the capacitor is two plates. On one plate we have positive charges, on the other one we have negative charges. Now let the plate with positive charges shrink to a point, and the other one expand it to infinity, and now we have a point charge. Using the transmission line model of the capacitor, we see that around this charged particle we have radiations. The electric field is from radiations traveling around the point. Radiations in such a way that the magnetic field is invisible. Start with a positive charge. We have electric fields radiating from the point. Suppose this electric field will change in amplitude. Then we know from Maxwell's equations that this will create a rotating magnetic field around the electric field. Now we have magnetic fields that are changing. On this side we have a magnetic field into the paper, and this will create a rotating electric field. And on the other side we have a changing magnetic field out from the paper, and this will create an electric field in the other direction. And we see that these new electric fields are in opposite direction to the first changing electric field. So this is this particle with the fields is a stable construction. It's self-regulating. The next step is to calculate the energy in the radiating encircling the electron. We can calculate the energy because we have radiation. I start with a small radiation element, and I go on and integrate to calculate the total the total energy in the fields encircling the charge, and then I use values for the electron. I have the charge Q, I have epsilon, and I have the radius of the electron. I have chosen the classical radius of the electron, and I use the formula I have derived, and the result is equal to the energy that is associated with the mass of the electron. This is my calculated energy, and this is the energy calculated from mc square. And this raises the question: if all energy associated with the electron is contained in the radiation encircling the electron, is there anything in the middle of the electron, or is there an empty space? If all energy associated with the electron is contained in the radiations encircling the electron, we can use this to explain the double-slit experiment. When we fire electrons to this slit, the radiations will squeeze through the slot, and on the other side they are reorganized, and the electron is traveling in different directions. But if we have two slots, one part of the radiations is going through this slot, and the other part is going through the other slot. And here on the back of the plate they are reorganized, but they are disturbed because we have a distance between the slots, and this gives this interference pattern. Now, if we try to measure how many electrons are going through this slot and how many is going through that slot, when we measure an electron, we reorganize the radiations, and now it looks like that the electrons are coming from this point and this point, because here the electrons are reorganized. But if we switch off the detectors so that they don't detect the electrons, they are not reorganizing the fields, and then we have the same pattern as when we had no detectors over here. The next step is to look at the electron in motion. When the electron is moving, the radiations are not going in circles, but in a helix. And when we make a helix of the circle, the radius will be smaller. And if we integrate the energy in the electron when we decrease the radius, we can see that the extra energy in this inner part is exactly the energy of movement. This gives a model of the electron. The electron itself is just radiations around some certain radius. When the electron is moving, the inner radius is smaller, and the energy stored in this area over here is the energy of movement. And this is what happens to every particle that builds up the object that is moving. So the energy of movement is stored next to the space in the middle.